August 12, 2018, NASA launched a spacecraft on a Delta IV Heavy rocket, which became the closest human-made object ever to the Sun. Its name was the Parker Solar Probe. Today, the data coming from Parker Solar Probe is showing scientists things about the Sun that were previously only theoretical. And this data raises an important question. How does the energy coming from the Sun affect our Earth? In this video, we'll calmly and clearly understand what the Parker Solar Probe is measuring, what this data means for Earth, and whether we should be concerned about any immediate danger or not. So whenever we look at the Sun, two things usually come to our mind. It's heat and it's light. But the biggest misconception people have is this, that the Sun is burning like a ball of fire, the same way coal burns on Earth. That's a myth. In reality, the Sun is made of plasma. Understanding plasma is actually very easy. In school, we're taught that matter exists in three states: solid, liquid, and gas. But in reality, there are four states of matter: solid, liquid, gas, and plasma. The easiest way to understand plasma is this. When you give energy to a solid, usually in the form of heat, it turns into a liquid. If you give more energy to that liquid, it evaporates and becomes a gas. But if you heat this gas even further, it turns into plasma. The temperature of plasma can range from about 1,000 degrees Celsius to millions of degrees Celsius. And the Sun is completely made of plasma. Because of this plasma, the Sun is able to provide us with such intense heat and brightness. Day exists on Earth only because the Sun exists. If the Sun were gone, the concept of day would not exist at all. Photosynthesis on Earth happens because of sunlight, and that's the reason you and I are able to breathe. Trillions of watts of electricity are generated on Earth every single day, only because of the Sun. Now you might be thinking, wow, the Sun sounds like an amazing thing, because it's absolutely essential for sustaining life. But besides its good side, the Sun also has a dangerous side that most people don't even know about. And before understanding that dangerous side, we first need to understand the structure of the Sun. Don't worry, it's very simple. First comes the core. Yes, this is the region where the Sun's energy is produced. Its thickness is about 175,000 kilometers. After the core comes the radiative zone, which is about 320,000 kilometers thick. Then comes the convective zone, with a thickness of around 200,000 kilometers. After that comes the photosphere, which is about 500 kilometers thick. This is the actual surface of the Sun. When we look at the Sun, most of what we see is the photosphere. Next comes the chromosphere, with a thickness of about 2,000 to 3,000 kilometers. This is where the Sun's atmosphere begins. After that comes the corona. Don't misunderstand. This is not the 2020 coronavirus. This is a part of the Sun's atmosphere, and it's massive. Its thickness can reach 2 to 3 million kilometers. But the Sun itself has a total radius of 698,000 kilometers, which means its diameter is approximately 1,391,000 kilometers. That's so large that all 8 planets of our solar system could fit inside it 3 times, and there would still be space left. Now you can imagine just how massive our Sun really is. Now let's understand why the Sun shines so brightly and what fuel it runs on. In very simple terms, the Sun contains a huge amount of hydrogen. Inside the Sun, hydrogen atoms are constantly moving around, and sometimes they fuse together. This fusion creates helium. When 1 kilogram of hydrogen fuses, it forms 0.993 kilograms of helium. The remaining 0.007 kilograms is converted directly into pure energy, which spreads throughout the universe in the form of heat and light. According to estimates, the Sun converts about 60 million tons of hydrogen into helium every second. If you do the math, this process releases around 3.78 multiplied by 10 raised to the power of 26 joules energy per second. That means the energy produced by the Sun in just 1 second is enough to power all of humanity for 1 million years. But here's the catch. The temperature of the Sun's core is about 15 million degrees C, and the temperature of the photosphere, the surface, is about 5,500 degrees Celsius. Now common sense would say that as you move farther away from the core, the temperature should keep decreasing. And that does happen, up to the surface. But what about above the surface? What should the temperature of the sun's atmosphere, the corona, be? Pause for a second and tell me in the comments what you think the temperature of the sun's atmosphere should be. Done commenting? Now listen carefully. The sun's core is 15 million degrees C. The surface is 5,500 degrees Celsius, right? But the temperature of the sun's atmosphere is more than 2 million degrees Celsius. That means the corona is farther from the core than the surface, yet it's far hotter. How is that possible? This is the mystery known as the coronal heating problem. And from here, the dangerous side of the sun begins. In Chapter 1, we understood that the sun is not just a glowing ball, but a highly active plasma system. Now the next logical question is, when the sun generates so much energy, where does that energy go? The answer is simple. The sun sends things out into space, and not just light. First, let's talk about the solar wind. Solar wind is a continuous flow of charged particles, mainly protons and electrons. These particles escape from the sun's atmosphere, the corona, and spread throughout the entire solar system. The important thing to understand is this. Solar wind is not an explosion. It's happening all the time. Sometimes it's slow, sometimes it's fast, but it never completely stops. Now here's a common confusion. People often think sunlight and solar wind are the same thing, but they are completely different. Sunlight travels at the speed of light, which is why sunlight reaches Earth in just 8 minutes. Solar wind particles, on the other hand, move much more slowly. They can take hours, and sometimes even days, to reach Earth. That means when something happens on the sun, its effects on Earth can arrive instantly, or with a delay. Now apart from solar wind, the sun sometimes sends out much more powerful events. One of them is called a coronal mass ejection, or CME. During a CME, the sun doesn't just release particles. It throws a large portion of its magnetic field into space as well. The difference is simple. Solar wind is continuous. CME is sudden. Solar wind is like background noise, while a CME is a powerful burst. Now there's one more important thing we need to understand. We often imagine space as a completely empty vacuum, but in reality, space is not empty. Space contains plasma, magnetic fields, and energy coming from the sun travels through all of this. This means that between the sun and Earth, there isn't just empty space. There's an active environment where energy is constantly moving. And this is where scientists faced a problem. Measuring all of this accurately from Earth was extremely difficult, because by the time these particles reach Earth, they've already changed. So if we truly want to understand the sun's behavior, there's only one option left. We have to go closer to the sun, and from this point, we enter the next chapter. When scientists were designing the Parker Solar Probe, their reason was very simple. The question was, what could be faster than CMEs and the solar wind? And there was only one answer: the speed of light. The idea was to place a machine so close to the sun that it could directly observe the sun's activity and send signals to Earth at the speed of light, so we could get an early warning. That's why the Parker Solar Probe was built. But there was a problem here. In the previous chapter, we saw that the sun's corona is about 1.5 million degrees Celsius. And logically, even if Parker were made entirely of iron, it would melt the moment it entered the corona. So how does Parker survive there? To understand this, we need to understand a bit of basic physics. Heat is mainly transferred in two ways: radiation and medium. Radiation, like infrared radiation, is universal, whether it's Earth or space. Infrared radiation follows the same rules everywhere. But the second factor, the medium, is flexible. For example, when we sit near a campfire, we feel more heat not just because of radiation, but also because of hot air. The fire heats the air, the hot air rises, and when that air flows past our body, we receive extra heat. But in space, this second factor doesn't exist at all. Space is almost a pure vacuum. The medium is practically negligible. That's why, even though the sun's corona has an actual temperature of 1.5 million degrees, Parker only has to deal with radiation. And to handle this radiation, a special white heat shield has been placed in front of Parker, which reflects direct infrared radiation. That's how the Parker Solar Probe is able to survive even while going so close to the corona. Now the next question is, was Parker built only to give warnings? Or is it also studying the sun? The answer is both. And this is where Parker stops being just a space mission. This is where Parker becomes a warning system. Parker didn't just show us what the sun looks like. Parker showed us how unpredictable the sun's behavior can be. Earlier, we used to think that solar storms were random. Sometimes they happened, sometimes they didn't. But Parker's data made it clear that beneath the sun's surface and inside its magnetic field, things are continuously building up. This means danger isn't created suddenly. It keeps growing quietly, and when it's released, it doesn't just affect the sun, but every object in space that lies within its influence. And yes, Earth is on that list too. So far, we have understood that the sun's danger doesn't come suddenly. It builds quietly. So now an important question arises. Has this ever happened before? The answer is yes, and many times. The most famous case is the 1859 Carrington event. At that time, electricity was very new. There were no satellites, no internet, no GPS. There was only the telegraph system. And then one day, a massive solar storm from the sun moved toward Earth. The result? Telegraph machines stopped working. In some places, sparks started coming out of the wires. Operators received electric shocks. And the most shocking part, the polar lights in Earth's sky were so bright that people could read newspapers at night. And all of this happened just because the sun released a violent burst of its energy. Now imagine, if this event happened today, electric grids would fail, satellites could be damaged, GPS, communication, internet, everything would become vulnerable. And the Carrington event was not a single case. In 1989, because of a solar storm, Canada's Quebec region experienced a complete blackout. In just a few minutes, the entire power grid collapsed. This means that the sun's impact is not theoretical, it is real, and it is documented. The only difference is, earlier, we were less dependent. Today, we are completely dependent. Without satellites, there is no navigation, no communication, no weather prediction, no defense systems, and the sun does not care how advanced we have become. The sun does what it has always done. The only difference is, now the damage can be greater. And that is why Parker Solar Probe's data is not just for science. It is a reminder that history can repeat itself. The point of this entire video is not that the sun is going to destroy Earth tomorrow or the day after, but to understand that the sun is not always calm. It is not just a fireball. It is a plasma system that quietly stores energy and sometimes releases it. And history has already shown us that when the sun becomes violent, its impact is not limited to space, but reaches Earth as well. Today, we are more advanced than ever before, but at the same time, we have also become more vulnerable than ever because satellites, power grids, and communication systems are directly dependent on the sun's behavior. That is why missions like the Parker Solar Probe are important, because they do not teach us how to control the sun, but how to stay prepared. Stopping the sun is not in our hands, but understanding the sun now is. And when we start understanding it, disasters stop being surprises, they become warnings. If you're interested in learning more unexplained and slightly uncomfortable truths about space, subscribe to the channel. And yes, if you haven't seen it yet, I've made a video where we discussed what different space objects in the universe might smell like. You'll find the link to that video in the description and the pinned comment.